Okay, this should be the last video, guys. Alright, so we are on example 1610, and this is given a situation of sort of what we've already kind of dealt with on the last example, where we are having to figure out acceleration and things like that. So we have to kind of go back and just really think about some kinematic concepts. So when I said, in Physics 1 that you would never get to, get rid of those or not think about those, I was not lying. So this is telling you that these plates are 2 centimeters apart, so like in the y direction, and then they are 4 centimeters apart in the x direction. So I don't really remember if you remember when we did projectile motion, we had to figure out stuff that went in the x direction before we could then take that answer and we could plug it into the y direction equations. Projectile motion is usually not liked because it's taking those kinematics equations and you have to think about it in both x and y. So it's what you have to do in this one. And you can see that this electron is entering in between these two parallel plates. And let me just ask you, if the electric field is going this direction, then what does that tell you about the charge of this plate right here? Well, those electric fields always point towards negative. So this would be negative and this would be positive, okay, because they're pointing away from this plate. And if you put an electron in between there, and an electron's a negative charge, what's going to happen? It's going to be repelled from this plate, right? But this electron has an initial velocity in the x direction. So this is wanting you to find the magnitude of the electric field that's happening between these two plates. Okay, so you have to kind of think about both x and y values. All right, so I'm going to go on over to our next slide and kind of write some stuff down. So we had this, I'm going to draw these plates again really quick. We had these two plates. They were 2 centimeters apart this direction. They were 4 centimeters apart this direction. And we know that the electric field is going like this. And there's an electron that's going in here and it's like barely missed the plate. Okay? So let's see, what else did it give us? It gave us that the initial velocity in the x direction was 8 times 10 to the 6th meters per second. And we know that the mass of an electron is 9.11 times 10 to the negative 31st kilogram. We know the charge of an electron is 1.6 times 10 to the negative 19 coulombs. So just some things that we might need. Okay, we are ultimately trying to find the electric field. So this is one of those that you have to use a few equations. And I know that that's always disliked. So if you think about something that has electric field in it, okay, we had a couple of those. We had this one, and then we also had this one. Okay, so in this, we are, if you think about it, we are given a distance in the x direction, and we're also given a velocity in the x direction. So think about some old kinematics. Remember, if you have a distance divided by time, you could find a velocity. Well, we have a velocity and we have a distance, so we could find time. So if we rearrange this to solve for time, like that, then we could take our x direction distance, which is 4 times 10 to the negative 2nd meters, divided by our velocity in the x direction. And the velocity that it gave us was 8 times 10 to the 6th meters per second. So the time that it takes to go from that one end to the other end, so 4 centimeters, is 5 times 10 to the -9th seconds. Okay, so now we've got a time. What would I use for time? Well, we had some kinematics equations that we could have solved for acceleration if we had time. And why would it be good to solve for acceleration? Because force is equal to mass times acceleration. Okay, so we could have something like that as well. All right, so let's try to go in that direction. We had a couple of kinematics equations. The big ones were like this. We had y was equal to y naught plus EOT plus 1/2 AT squared. And then we also had v squared is equal to v naught squared plus 2a times the change of y. Why did I use y instead of x? Well, we already extinguished our x information up here. As soon as that electron goes into the electric field between those two plates, what direction does it start to go then? It starts to go in the y direction. So that's why we are using y's. Now, which one of these involves time? The first one. So this one's eliminated. You are solving for acceleration. Okay, so we're solving for acceleration. Now, let me ask you about this right here. Do you use the initial velocity that it gave you in the problem? No, because that was the initial velocity in the x direction. We are now doing kinematics in the y direction. So as far as when that electron first entered in, it had 0 velocity in the y direction. Okay? It was only going straight x. You can see that in that picture. So that's 0. Okay, so I just wanted to point that out before we went on. So now we can just solve for A. So A is equal to 2 times y divided by t squared. Do we have a y value? Yes. Now, this distance right here, that distance right there is 2 centimeters, but where does it look like the electron is entering? It's entering right in the middle. Okay, so our y value isn't 2, our y value is 1 centimeter. Okay, so you've got 2 times 1 times 10 to the -2 meters divided by your time. Okay, squared, and that's equal to 8 times 10 to the 14th meter per second squared. Okay, that's your acceleration. Now, we are trying to find the electric field, and I actually wrote this wrong over here. Sorry, let me fix that really quick. This is actually force is equal to charge times electric field. I had those backwards, but force is still equal to mass times acceleration. So you can find the electric field by doing force divided by Q, which is mass times acceleration, divided by Q, which is doable now. We've got 9.11 times 10 to the -31st kilogram times the acceleration, which is 8 times 10 to the 14th meters per second squared, divided by the charge of an electron, which was 1.6 times 10 to the -19th coulombs. Okay, do all the math there. You should get that this is, oh, and this is a negative, by the way, because it's an electron. So this got 4.55 times 10 to the third newtons per coulomb. And that negative also is saying what's the magnitude of the electric field. Well, which direction is the vector going up here? These vectors up here are going down. Okay, so again, that tells you the direction. All right, so that's example 1610. And then we're on the very last bit here. It's saying that conductors in electrostatic equilibrium. So polarized materials are when they are, you've got poles, right? So you've got these positive, negatives. So they're conductors because they contain highly mobile charges, meaning that those electrons can flow freely through. And that's pretty cool to me, I think. It's useful to examine the distribution of charge, whether the conductor has a net charge or lies in an externally applied field. So we restrict our attention to a conductor in that situation whenever the charges are at rest. So kind of like at the very beginning of the PowerPoint where all of those charges had kind of gone to separate parts of the sphere and just sort of become in equilibrium state. That's electrostatic equilibrium. And that's the end. The PowerPoint that you have on the beginning that you might have printed out already, there were a few more slides on electrostatic equilibrium, but I went ahead and took some of those out. So this is it for chapter 16. We're going to have a quiz on Friday. So if you have any questions about any of that, let me know. And then there's some homework that's on Connect as well. Alrighty. I will